All right, let's get right into it. In the world of AI, breakthroughs happen all the time, but it is so rare for a single academic paper to cause a multi-billion-dollar panic on the stock market. Well, today, we're talking about the one algorithm that did exactly that, Google's TurboQuant.
The second this research paper dropped, the reaction was just immediate and brutal. I mean, this quote from a TechEye news report really says it all. We are not talking about a little dip here. This was a legit shockwave that just ripped through the heart of the entire AI hardware supply chain.
And the damage was staggering. In just 5 days, Micron's stock absolutely plummeted, down over 24%. SK Hynix dropped 20%. And you gotta remember, these are the giants. They build the high-performance memory that powers this entire AI revolution. The market was completely terrified.
So that brings us to the big question, right? How on earth could a piece of software, just a compression algorithm, pose what looked like an existential threat to these massive hardware companies? To get that, we need to talk about a critical bottleneck in modern AI.
See, the problem that TurboQuant was designed to solve is something that developers and AI companies fight with every single day. It's the memory bottleneck. And it all comes down to something called the KV cache.
So what is a KV cache? Well, the easiest way to think about it is like an AI short-term memory. As a large language model is generating text, it's storing all these little intermediate calculations for every single word it's already seen. Now, this makes things fast, but the cache just grows and grows and grows, eating up a ridiculous amount of super expensive VRAM.
And we are not talking about a small amount here. The KV cache for just one person running a pretty normal, mid-sized model can take up 4.6 gigabytes of VRAM. Now just try to imagine scaling that up to thousands or millions of users. All of a sudden, this short-term memory problem becomes the single biggest cost and the biggest hardware problem for running AI at scale.
So this is the exact problem Google's researchers went after. And they came up with this really clever two-step compression trick to dramatically shrink that KV cache without, or so they claimed, losing any quality at all.
The whole process is this kind of slick two-step. The first step is a random mathematical rotation. Okay, think of it like shaking a box of sand to get it perfectly level. This rotation just reshapes the data into a nice, predictable bell curve. And once the data is in that predictable shape, step 2 is a piece of cake. They use an optimal rounding method to squeeze every value down to just a few bits. And they add a tiny 1-bit correction just to make sure the accuracy stays high.
And the result was absolutely stunning. A claimed 6x reduction in memory usage. That 4.6 gigabyte cache, it could now fit into less than 1 gig. But here's the kicker, the part that really shocked everyone. They claimed they could do this with zero loss in the AI's output quality. It's like getting JPEG compression for an AI's brain, but without losing a single pixel. And that is what spooked the market.
But here's where the story gets really interesting. The open source community, like they always do, jumped on this paper immediately. They started building their own versions to see if Google's claims held up. And what they found was pretty surprising.
It turns out that the centerpiece of the paper, that clever little 1-bit correction method, it had a huge flaw. Yeah, it worked great for stuff like vector search, which is kind of like a super-powered Dewey Decimal System for data, but for the very specific way that AI models use what's called attention to focus on important words, it actually made things worse. And this really gets to the heart of it. The paper's method was designed to be mathematically unbiased, which, sounds great, but what it actually did was introduce a bunch of random noise or what's called high variance. The community figured out that an AI's attention mechanism hates variance. It just blows it up exponentially. So they found that by just throwing out that second step and using a simpler, lower variance method, they got way, way better results.
And hey, you don't have to take my word for it. The proof is right here. Developers ran a classic needle and a haystack test. They hid a secret code inside a super long document and asked the model to find it. The results? Undeniable. The community's simpler fix found the secret code exactly. The paper's official method missed it completely.
But the community didn't stop there. They also realized that in the keys and values cache, the keys and values do totally different jobs. The keys are what guide the model's attention. They need to be really precise. The values hold the actual content, where tiny errors kind of cancel each other out. So they started giving more bits to the keys and fewer to the values, and what do you know, they got even better results with the exact same memory budget.
So this brings us all the way back to that market panic. Now that the algorithm was not only validated but actually improved by the community, Wall Street was left to basically fight over what this all meant for the future of memory chips. And two main stories emerged. The bear case was simple. If every AI needs 6 times less memory, well then companies are going to buy 6 times fewer memory chips. Boom, demand destroyed. But the bull case brought up this old economic idea called the Jevons paradox. And it argues that when you make a resource way cheaper and more efficient, you don't use less of it, you use way, way more. So if AI becomes 6 times cheaper to run, we won't just run the same amount, we'll run 100 times more, which actually means we'll need even more hardware overall.
And pretty quickly, big firms like Morgan Stanley sided with the bulls. Their analysts pointed out, hey, TurboQuant only affects the KV cache for running an AI. It does nothing to the insane amount of memory you need for training one. They just saw it as a natural step forward that would drive more AI adoption, not some industry-killing event.
So after all that, all the tech deep dives and the market drama, what are the big takeaways? What does this actually mean for you, for developers, for businesses, for anyone who's paying attention to AI?
Well, first, running AI is getting much, much cheaper. That's a huge deal. Second, this means you're going to be able to run models with way longer memory, longer context on the hardware you already have. Third, this whole story is just an amazing win for open source. It shows how a global community can test, validate, and even improve on research from the biggest labs on the planet. And finally, it's a huge reminder that software really matters. A clever algorithm can give you performance gains that are just as big as a whole new generation of hardware.
And that leaves us with one last really fascinating question to think about. For years now, the AI race has been all about hardware, this massive gold rush to build bigger and faster chips. But as algorithms like TurboQuant show us just how much power you can unlock with software, you just have to wonder, is the focus of the great AI gold rush about to shift from silicon to code?